Sitting here, respected chairman, engineers, professors, and other affiliated members of SPARRSO, Assalamu alaikum and very good day to you all. I am Mohammad Abrar Jahin, a certified supply chain analyst, currently pursuing my BSc in IP third year at Kuwait. I am a former research intern at UIT, the Arctic University of Norway, and currently interning in Physics and Biology unit under the renowned Professor Jonathan Miller at Okinawa Institute of Science and Technology, Japan. My intended research project for SPARRSO is titled Disaster Damage Mitigation by Multispectral Remote Sensing Satellite Image Data Analysis, a Deep Learning Approach. Since I've got a limited time, so I want to automatically detect road and building from satellite images that can facilitate disaster management in different ways. In a nutshell, during cyclone, I can locate escape routes, evaluate the damage, and evaluate the effects. And during earthquake, I can perform building stock assessment, hazard mapping, planning routes for search and rescue, damage assessment, evacuation planning, identify sites for rehabilitation. During fire, I can identify fire-prone regions and assess the extent of damage. During flood, I can warn early, rescue planning, spatial planning, mapping flood-prone locations, etc. We all know devastated locations frequently have limited supplies. This must be done quickly and efficiently to identify the most impacted regions. Since most of these disaster mapping efforts are made manually, they are time-consuming and erroneous. When a disaster strikes, the public's need for road information becomes crucial, and processing this information may assist to reduce the number of people getting injured. Because of this, road extraction is essential to protection of our people and readiness, awareness, and preparation of a government in the event of an emergency. So, international organizations' damage maps still rely on visual interpretation, which takes a lot of time and effort. Detecting buildings and other urban structures are essential for urban demographic modeling. Building detection from satellite images is a challenge for acquiring bulk urban data, rapid assessment of building damage, and obtaining specific information on the geographical distribution of urban settlement. Moving on, what is my research objective? Well, I want to mitigate disaster damage by locating the most disaster impacted regions utilizing deep learning models like convolutional neural network, DesNet image VGG, etc. I will build an automated crisis response and enhanced map exposure for accessibility by retrieving roadways and street networks from satellite images. Moreover, using deep learning model, I will automatically detect buildings from satellite images for urban data collection remotely and through information gathering on urban settlement spatial dispersion. I will also formulate a novel disaster metric. This is disaster effect metric to coordinate the most disaster prone regions by improving the model accuracy. Here you can observe the two side-by-side images. The left one indicating the road extraction dataset and the right one indicating the building segmentation dataset. Both have been obtained from DeepGlobe. Moving on, what is the state of the art review? For road classification in satellite image processing, many unsupervised learning techniques like principal component analysis were initialized for feature detection. When CNN was initialized in deep learning, because of its capacity to collect a huge amount of spatial information, encoder-decoder dependent architectures were commonly employed. Moreover, DesNet 18 backbone and focal loss integrated with refined deep lab architecture resulted in superior results. Well, simple rotation was implemented as data augmentation technique after binarizing the findings at the set threshold of 128 in order to establish a baseline for evaluating the network. But the research gap was no post-processing was applied to the results. Using this configuration only, 54.5% intersection over union was obtained after 100 iterations of training. Multitask approach was used to optimize the predicted road network connectivity. Moving on to building segmentation dataset, in which two layers of locally linked neural network accompanied by a layer of completely associated neural network was used, and then the modified misregistration noise and loss function was used to consider omission noise, allowing for translational noise. LSNet's convolutional layers were utilized for feature extraction that was then fed into the support vector machine classifier, which classified pixels into the building and non-building categories too. Then, for extracting road and building, CNN-based techniques were also used by evaluating IRR and G data with 5 convolutional layers and augmenting it with normalized digital surface model. The FCN8 segmentation network was also employed. Segnet and UNet techniques were also used to segment buildings in other computation solutions. What are the research gaps and challenges? For road classification, post-processing approaches other than basic thresholding might result in more linked roads. So, with varying widths, bifurcation obscured by topography, cloud, or other weather conditions makes it really difficult to detect road segments, since it is inefficient to obtain the remote relationships between road segments in the images, which are really necessary to extract road connectivity. Using just CNN for this issue is not an option. For building segmentation, extraction of a building's footprint may be utilized in conjunction with DSM data to construct 3D representations of the building structure that have been detected. I want to propose a novel metric that can extract the most disaster impacted building features that might increase in deep learning model accuracy. Due to the adjacency to other features, the borders of buildings are frequently incorrectly classified, resulting in inconsistent extraction results for structures and their originals. To increase the accuracy of building extraction findings, further study is required. Moving on to methodology. For deep globe road image dataset, I will utilize the computationally efficient spin module, which will be connected to the CNN. For road segmentation from satellite images, I will build a network of stacked hourglass modules and spin pyramids. Fast network convergence is possible by spin module, makes it really easier to train CNN high-resolution satellite images. I will additionally use SegNet, UNet, LinkNet, hourglass, stacked hourglass, then Beta and his colleagues models on this dataset to better comparison with my model to their models. Well, for building prediction dataset, I want to employ an average ensemble from 3 UNet models, one of which is a deep neural network model for image segmentation to extract building footprints from an 8-band multispectral image. OpenStreetMap data will be integrated to improve accuracy to building footprint prediction. Well, each of the 4 areas will be used to train an ensemble classifier. Small items and densely populated areas may be too challenging for the algorithm. This is the limitation. Well, so for evaluation, I'll be using intersection over union. I'll be taking its mean for road image classification, and for building image segmentation, I'll be using the mean of the F1 scores. That is basically the mean of the 4 datasets of 4 individual regions. So what is the outcome? From satellite images, road extraction will help us to identify the connection between sites and assist us in the automation of navigation, the mitigation of natural disasters, and traffic control automation. So my model can be readily inserted into a CNN structure after a convolutional block, and my network's convergence rate will be reduced to half due to the spin's acquisition of highly contextual data, which saves the significant amount of runtime during training. And using large-scale high-resolution data like satellite images to train CNNs is very beneficial because of this feature. Well, what is the outcome of building detection? It plays a critical role in land planning, mapping, and reconstruction after a natural and man-made disaster. More than just one feature may be tied to a factor for surviving structures, like the number of people who died, the number of people who were displaced, the amount of property that was destroyed. Post-disaster reconstruction also takes into account the extent of damage. My approach to building detection reduces overfitting, time, and space complexity. The detection of structures in satellite images for disaster sites is critical for disaster prevention and reduction. Moving on, what is the time frame? Well, I have shown the breakdown of my whole overall project into the subsequent subsections along with the expected completion time given in months. I will require the additional 1.5 months for manuscript preparation. Since I am all familiar with manuscript drafting and article publishing in quartile 1 journal, so I won't take time greater than 1.5 months for that. So in total, I'll be requiring approximately total of 11 months for the whole completion of the project. Moving on. My monthly budget depends on the following factors: the availability of the dataset, complexity to develop the model, computing power to train the model, infrastructure required to produce the model. Well, there are some particulars I have mentioned here as the budget inclusion. I'll use Amazon SageMaker Studio Notebook for downloading the building segmentation dataset, image processing, and for exploratory data analysis. I'll use it for the first 6 months. Then I will use the Go Cloud subscription for Vertex AutoML image training model and prediction model individually, and I have estimated their individual costs, and I'll use it for the next 4 months. So since we all know that satellite image processing requires a heavy task and it's really time consuming, computationally costly, so it is not possible to compile this course on local computers. Fortunately, I have got an rare access and unlimited access to Japanese OIST scientific supercomputer Deco cluster, so I won't require any additional computing resources. That's a plus point. Additionally, I require a conference fee. This is for one-time conference fee, and I will require it only for the last month, and I won't be requiring the previous budget inclusions for the last month. I will only require the conference fee for the last month. So the total monthly budget amounts to 28,400 Bangladeshi taka. this is feasible, this is achievable. Thank you everyone. Thank you for having me. Thank you for having patience. Thank you.